Namaste students, how are you? Hope you are doing well. You are always cheering up and you will be happy spending all the time in your house, eating for 24 hours, taking rest. But now you have little bit of classes in between. So we have started refraction, you know it's a continuous process. And a few things about refraction we have already studied, about Snell's law and refractive index and lateral shift, normal shift. These are all the consequences of refraction. If light ray would not have bent as it travels from one medium to another, we were not able to see any types of normal shift or lateral shift. So let us recap a little bit about what we have studied. One is lateral shift. We know that before that we will see how does a ray of light change its direction and how do we measure it in terms of refractive index. So if your ray of light is incident on a media, if I is the angle of incidence and R is the angle of refraction, then we define refractive index. Suppose this is the refractive index of the second medium with respect to R. So this is the refractive index of the first medium with respect to R. Then we write sin I by sin R is always defined as the refractive index of the second medium with respect to first, and which can also be defined as the ratio of refractive index of the second medium only with respect to R. Now both are not in either 1 or 2. Neither of them are R, they are different media. So if you keep this medium with respect to R, then N2 is the refractive index, and if you keep this medium with respect to R, then N1, and which is also equal to V1 by V2. Now you cross multiply these two, what do you get? And that is called general law, that is also Snell's law. N1 sin I, refractive index into sine of the angle, refractive index into sine of the angle, N1 sin I is equal to N2 sin R. So this is the formula which we are going to use again and again in the future. Okay, right. And you know that when a ray of light travels from one medium to another, because of its refraction nature, there is a bending like this, and if these two sides are parallel to each other, then definitely the outcoming ray will be parallel to the original direction, and if this is parallel to the original direction, this perpendicular distance is called lateral shift. Lateral shift is the shift in the position of the ray of light, or it is the perpendicular distance between the original direction and the emergent ray when a ray of light undergoes refraction through a parallel sided medium. That is lateral shift. So lateral shift is one of the consequence of refraction, and formula for lateral shift, of course this is not in the syllabus, T by cos R into sin I minus R. So that is the amount of lateral shift, that is perpendicular distance, it is measured in meters. So lateral shift is T by cos R into sin I minus R, where T is the perpendicular distance between the two faces where the refraction is occurring. T is the perpendicular distance between the two faces where the refraction is occurring. I is the angle of incidence, R is the angle of refraction. That is the formula, but you need not worry about this for the theory. Okay. Now, so another consequence of refraction is normal shift. Any things kept inside the denser medium appear to be shifted upwards. That is a common thing, and you know a coin kept inside a beaker appears to be shifted up. Suppose this is the coin. When it is viewed normally, you will see that this coin is at some other position. You feel that it is not here, it appears to be shifted upward. So when a bird looks into water, the fish may not be at the same place where it is. It appears to be shifted somewhere else. So the bird should be very intelligent enough to catch the fish, because fish will not be seen at the same place where it is. But it has a natural instinct how to catch the fish and all. Now, where this coin appears to be, apparent shift in the object position kept in one medium viewed normally from the other medium is called normal shift. Okay, so you have to consider one ray which is moving normally, and angle of incidence is 0 because this ray is along the normal, because we measure all the angles with respect to normal. So this ray is along the normal, angle of incidence is 0, refraction is 0. Take another ray of light, incident at some angle, say this is water and this is this is air, then the ray of light bends away from the normal, denser to rarer medium, velocity increases. So another ray of light considered here, it will also bend away from the normal. For a person observing from outside, these two rays appear to come from a point here. So this is the direction along which it is a line which is projected backwards. So this becomes the image and this becomes the object, and if I name all the distances, this is the normal shift, normally viewed shift. And what about the other one? Other one, this is apparent depth, the depth at which the object is seen. It is not real, it is a feeling only, it is not real. And this is real depth. Okay, this is real depth. Okay. So what is the relation between refractive index of the medium with respect to air and real depth and apparent depth? Refractive index is equal to real depth divided by apparent depth. So this is the formula for refractive index. So you must know this. So this here we have stopped in the previous class. Refractive index equal to real depth by apparent depth, and you know that refractive indexes are not having any unit, depth in meters, so it gets cancelled, no unit. Now remember, do you have any sir, here in this formula we don't get anything which corresponds to normal shift. So can I have a formula for normal shift? This is in the syllabus, next formula is not in the syllabus, but you may have that very easily. So n is equal to, so shall I write this? Suppose if I take the normal real depth as the T or D, something like this, real depth, then normal shift as some ns, how can I write it? Refractive index n equal to real depth, that is D, divided by apparent depth. Apparent depth can be written as real depth D minus normal shift. Am I right? From this total depth, if I subtract this one, I get this one. So D minus ns. Is it so? Okay, that is refractive index. Okay. Okay, here, here now if I continue this one, I will invert this, invert the formula. So that implies 1 by n, 1 by refractive index of the medium where the object is present. 1 by n is equal to D minus ns by D, right? Real depth minus normal shift. Now if you divide this by D, what you will get? That implies 1 by n is equal to 1 minus normal shift by real depth. D by D minus ns by D. So that implies what is okay, I will bring ns by D to this side, 1 by n to the other side. Normal shift by real depth to the left hand side, 1 minus this, that is equal to 1 minus 1 by n. So what is normal shift? Normal shift is, so shall I write it? I will adjust it here. Normal shift is equal to the real depth into 1 minus 1 by n. So this is the formula for normal shift. Of course, you need not strictly remember this formula. You will get it from this. So this is the formula for refractive index, real depth by apparent depth. And this is the formula for the case when the object is kept in the denser medium, viewed normally from the rarer medium. All the things kept in the denser medium appear to be closer and closer. Whereas if you do the other way, go inside the swimming pool and look into the objects outside, they appear to be far away and far away. In such a case, you can have the formula as refractive index is equal to apparent depth by real depth. So you will have to change the formula. Of course, these are all needed not for theory, this one and this one. When you go in a little bit advanced towards the entrance examinations, all these things are needed. So here, apparent depth by real depth, this is the case when you are in denser medium, observe the objects in the rarer medium. And one more thing is, sir, this is air we have considered. Suppose this is not air. So I will call this as the refractive index of the medium where the object is say kept. And refractive index of the medium where it is viewed, then this is Nk by Nv. This is the formula, right? So Nk by Nv. So this formula, don't write this in the answer paper, just to remember. For example, if the other medium is not air, suppose other medium is air from where you have observed, viewed, refractive index of the medium where the object is viewed. If it is air, then this becomes 1. You can replace this as n, no problem. But suppose the problem contains two different media, the observing media is not air, even the other one is not air. Then this is the strict followed formula. Refractive index of the medium where the object is kept, divided by refractive index of the medium where it is viewed, then real depth by apparent depth. That's how it is taken. And if you are asked to write the examples for normal shift, coin appears to be shifted upwards, and the bottom of the swimming pool appears to be shifted upwards, and a pencil kept in a beaker containing water appears to be broken. How it is so? You just imagine that, suppose you have a beaker containing water, and if this is the stick or the pencil which is kept and it is filled with water, just analyze it like this. Why does the stick appear to be like this, broken here, from here onwards, like this? Reason is very simple. Now you paint this stick with the different colors here. You paint this, paint it here and here. Imagine that the whole stick is made up of different pieces. Now each piece from the surface of water, each piece is at different real depth. Real depth for this piece is this one, real depth for this piece is this much, real depth for this piece is this much. So different pieces will have different real depth. When you have different real depth, same refractive indices. Even if you view the pencil from here to this point, here to this point, here to this point, refractive index of this medium and this medium are remaining the same. So these two will not change, and real depth keeps on changing. So when real depth keeps on changing, apparent depth should change, so that you have to keep this ratio same. That means real depth, if it is more, apparent depth is also more. This appears to be shifted here. This point of the pencil appears to be shifted here. For this point of the pencil, real depth is less, apparent depth is also less, not this much. This part of the pencil, real depth is less, apparent depth is also less, it is not this much. So apparent depth keeps on changing. The whole stick appears to be shifted here. Each and every point of the that stick appears to be shifted upwards. So that is the beauty of normal shift. So the whole stick appears to be broken, because we expect the stick to be like this inside the water also, but it doesn't appear so, it will be appearing here. So that is about normal shift. Okay. Now another important concept is total internal reflection. We will move on to that. What is total internal reflection? You might have heard about this word in your lower classes. You will have to go a little beyond this, that's all. Now, whenever a ray of light travels from denser to rarer medium, it bends away from the normal. We know that consequence. Now, if you go on increasing the angle of incidence, then the angle of refraction should go on increasing. So, denser to rarer medium movement means velocity increasing. Rarer medium, it should have more velocity. Light should have more velocity in rarer medium. I will take water. Inside the water, imagine there is a bulb. And bulb emits light in all the directions. So you consider different rays of light moving from denser medium N2 to rarer medium N1, sorry, N2 here. Denser to rarer medium. Consider one ray of light which is incident. Say this may be air and this may be water. You are looking into the rays of light coming from water. A ray of light incident normally like this, along the normal, angle of incidence is 0, angle of refraction is also 0. It moves undeviated. It moves simply away from, it moves away without any bending. We say in a single word, the ray passes undeviated, without any deviation. Okay, because I is 0, R is also 0, there is no bending. Take a ray making an angle like this, because bulb will emit many rays. There is no restriction. When the ray of light is incident at some angle, imagine a normal here, and that for that normal this makes an angle I, and since the ray is moving from denser to rarer, its velocity is increasing, so the ray, instead of moving in the same direction, it will be thrown away like this. This is the angle of refraction. It bends away from the normal. Now there may be still one more ray of light which is moving like this. So what happens to this? For this one, definitely angle of incidence will be more than this angle because it has bent a little more, and its angle of refraction will also be more than the previous case. So I call this as I dash and R dash. So if you go on tracing such rays one by one, what will be the condition then finally? Consider one more ray of light like this. Sir, what happens to this ray of light? And we will assume that this ray of light moves very, very close to the surface, because as we increase the angle of incidence, angle of refraction should keep on increasing. Finally, you can find a ray which is moving very, very close to the surface like this. Very close to the surface, such that I can write this ray to be almost moving at 90 degrees, right? It is not exactly 90 degrees, it cannot be 90 actually, but we take it as 90 and we say that it is a critical condition. What do you mean by critical? You can't have it in practical. It is very difficult to have a ray of light at 90 degrees, undergoing refraction at 90 degrees. I will say why it is critical. So I call this particular angle where the ray after refraction grazes the surface. It is grazing the surface. What do you mean by grazing? Cow is grazing the surface because it is moving parallel to the surface, and this is moving parallel to the surface, almost 89.999 degrees, and so almost 90 degrees. I call this angle a special angle called critical angle, where this is critical angle, where angle of refraction is 90 degree. I didn't call this as critical angle because this is an ordinary refraction. We have some angle of incidence, we have some angle of refraction which is greater than angle of incidence. Similarly here, but this is a special case. So if you take a ray of light and make it to fall at some particular angle which is traveling from denser to rarer medium, then after refraction it moves parallel to the surface. Sir, why didn't you write it parallel? Okay, in the examination when you draw that, it's a critical condition, you are explaining that it is parallel. I will show it like this, parallel to the surface. But this is not possible in reality. You know, principle of reversibility for the ray of light. If you put a ray of light like this, it should move like this. Now if I turn this ray of light, I will keep a small plane mirror as I do usually. Take a plane mirror, keep it like this. What happens? When the ray of light falls normally on the plane mirror, it will be returning back. So from here onwards, will it follow a different path like this, or will it follow the same path? It follows the same path. According to principle of reversibility, or light follows the principle of reversibility, if the ray of light is returned back in the same path, it returns here. It undergoes the same angle of refraction. So if this is the angle of incidence here, it undergoes the same angle of refraction here. For this ray also, it follows the same path. If so, if we argue that for some angle of incidence called critical angle, the angle of refraction is 90 degree, exact 90 degree. The ray is moving parallel to the surface. Let us assume like that. If it is so, you go to the principle of reversibility. Suppose this is surface of water. Take a laser beam, put it like this. Then how come the laser beam know that it should enter here? It will move parallel to the surface like this. So if you have a glass slab, and if this is the normal, if you put a ray of light like this parallel to the surface, how come this laser beam know that it should come like this? It cannot be, because it will move parallel to the surface like this. Suppose you have drawn normal here, you expect the laser beam to come inside here. Not possible. How come the laser beam know that the normal is drawn here? No, not at all possible. That means this angle is not exactly 90, but theoretically we take it as 90. It is a very small angle. It is moving parallel to the surface and falling here. Now where does it touch the surface? It enters in. This is not exactly 90, but we will write it as 90, very close to 90. So theoretically defining, how do you write this? So that's why I don't rub this. I take it as 90. So what is critical angle? When do you get the critical angle? Critical angle is the angle of incidence for which angle of refraction is 90 degrees. You have to define critical angle taking this as reference. So critical angle is the angle of incidence. It is the angle of incidence. Is it the angle of incidence for, is it a general angle of incidence? Is it or is it a special angle of incidence? Yes, for which angle of refraction is 90 degrees. I wrote this on the board because you commit a mistake always. You understand this, you know what it is, but in the examination you will write critical angle is 90 degrees. It is not 90 degrees. Critical angle is this one, and this is 90 degrees. You have to define critical angle in terms of what is the refraction process at that moment. Critical angle is the angle of incidence for which angle of refraction is 90 degrees. That is almost 90 degrees. So that is critical angle. Okay. Now sir, our curiosity doesn't stop at all. If you take a ray of light from denser to rarer medium, it bends away from the normal. If you go on searching different rays, at one condition it becomes almost parallel to the surface. Still, if you increase the angle of incidence, what happens? I'll take one more ray of light which is incident like this. What is its condition? What is the situation here, sir? It's interesting now. Instead of going outside, it undergoes reflection. It comes like this. Now reflection has started. Up to this we had refraction. Up to this we had refraction. And here onwards it is reflection. Sir, for reflection to occur, is this a mirror? No, it's a surface of glass, surface of water or surface of glass, and the light ray should have moved outside, but this angle has made it to come back. This angle is the angle greater than critical angle. Now what is this? This is following the law of reflection now, so this should be IC, I greater than IC, this one. So if the angle of incidence is greater than the critical angle, so I have to have arrow mark here, greater than the critical angle, more than this one now, the ray reflects back to the same medium, and we call it as total internal reflection. So you may be asked to define what is total internal reflection. The case where when a ray of light travels from denser medium to rarer medium, if the ray of light is incident at an angle greater than the critical angle, the ray reflects back to the same medium. This process is called total internal reflection. So you have to explain the story, what has happened. Then you have to say that this is total internal reflection. So you have to start from once upon a time. Then you have to stop at they lived happily for a long time. So what is once upon a time? When a ray of light travels from denser to rarer medium and is incident at an angle greater than critical angle, that condition also must be mentioned, and is incident at an angle more than the critical angle, the ray reflects back to the same medium and instead of undergoing refraction. That process is called total internal reflection. And you may be asked to write conditions like this. A question may be like this also. What are the conditions required for total internal reflection? Can total internal reflection occur in all cases? No, not possible. Condition 1. Ray must be trying to move from denser to rarer. Ray must be tending to move from denser to rarer medium. It should try to move from denser to rarer medium. First condition. Second one, angle of incidence must be greater than critical angle, because you know, even if it is trying to move from denser to rarer, if the angle is less than critical angle, there is refraction, there is no total internal reflection. So conditions required for total internal reflection are, the ray must tend to travel from denser to rarer medium, and angle of incidence must be greater than critical angle. At the critical angle, you know what happens, right? So this is total internal reflection. So what is total internal reflection? What are the conditions? Very, very important question. And what is critical angle? Another important question where you usually commit mistakes, and you will be in a mood that I know everything about this, but when you write the sentence you will go wrong. Okay, now, so critical angle is the angle of incidence for which that ray of light undergoes refraction at 90 degrees. Now, sir, what is this critical angle value? I have water and air. What is the critical angle value? Is it same for glass and air? No, it depends on the refractive index. So if you take a glass block and if you want a ray of light to come back, what is the minimum angle needed? And if you have water and air, what is the minimum angle needed so that light ray undergoes total internal reflection? It has to be paired now. How? What is the relation between refractive index of the medium and this critical angle? This pair of media has got how much critical angle? And another pair of media, and what is the relation between N1, N2 and IC? That is important now. So obtain the relation between refractive index of the media and critical angle. Very simple derivation. Just you have to apply Snell's law, that's all. So start again from once upon a time. There were two media, one is denser and another is rarer, and they were living happily, and so like this. And once a ray of light came to the denser medium and it started moving towards rarer medium like this, and that was incident at an angle called critical angle, for which angle of refraction is 90 degrees. And you have to show an arrow mark here because you have to say that the ray of light is moving away like this. So consider two media, N1 and N2. A ray of light is incident through the denser medium N1 and it is moving towards the rarer medium N2. But now since the angle is critical angle, the ray of light undergoes refraction and moves parallel to the surface, almost parallel. I want the relation between this one and critical angle, correct? Okay. Apply general law of refraction. You know that in general law, refractive index into sine of the angle, refractive index into sine of the angle. So they must be equal. So N1 sine IC must be equal to N1 sine IC must be equal to N2 sine 90. You remember this, right? So if you have a refraction process like this, if you have a refraction, any type of refraction, so if the ray is undergoing refraction like this, then N1 is the refractive index here, N2 is the refractive index here. With respect to air, everything, this one when it was with respect to air, refractive index, this one when it is with respect to air, this is I and R. N1 sin I is equal to N2 sin R, most used formula in the optics chapter. Okay, so we have applied this, N1 sin IC, N2 sin 90. So you know, I will jump here now. N1 sin IC is equal to N2. What is sin IC? N2 by N1. What is critical angle then? Critical angle is sine inverse of N2 by N1. Okay, so critical angle is the sine inverse of refractive index of the rarer medium to the refractive index of the denser medium. You see here this ratio, it is the refractive index of the rarer medium to the refractive index of denser medium ratio. Sine inverse of N2 by N1, IC is equal to a small derivation, right? Now shall we minimize this formula to a little extent? Shall we minimize this? How to minimize this? You can minimize this like this. Now let us take that this medium is air and this is a medium of refractive index N. Then what will happen? N2 is 1 now because air has a refractive index 1. Because refractive index of air can be calculated as the ratio of velocity of light in air to the velocity of light in the medium. C by C, 1. This is the minimum refractive index. So critical angle can also be obtained by sine inverse of N2 refractive index of the rarer medium, that is air, divided by refractive index of the denser medium, N. So IC is equal to sine inverse of 1 by N. So this formula can be used, when the other medium is air. If the first medium is, okay, the denser medium of course you have to take other than air, and the next term is air, sine inverse of 1 by N. Now let me see one application of this, total internal reflection. One application. So one application is optic fiber. Optic fiber cables. So where do we use total internal reflection? What are optic fibers? Optic fibers are the small cables. And one of the advantage of total internal reflection is, you see, if you take a mirror like this and make a ray of light to fall and get reflected like this, 100% of the light is not reflected. Up to about 90%, 95%, that's all, even if it is the best mirror, not 100%. But in total internal reflection, 99% of the light is reflected. The amount of light that is absorbed or lost is very, very less. So why can't you use this type of reflection where almost all the light is reflected back to send the signals? What type of signals? You convert electrical signals into optical signals. Why can't you send it? That is made use of in optic fibers. So optic fiber contains some cables. What type of cable? Solid cables. Suppose you take a glass rod. For example, this chalk is a solid rod. If it is made up of glass, it is transparent, right? Or fiber, plastic, it is transparent. So we have such a type of cable like this. Okay? So a cable like this. This is made up of one material, and its refractive index is of one value. And this should be having more refractive index. So this is not hollow, this is solid. And to this cable, it's a flexible cable. It may be made up of fiber. If it is fiber, then you can bend it to up to a certain extent. It is coated with another material of lower refractive index. It is also transparent. So optic fiber is a cable which can be bent into different angles, and it is made up of a core, and this is called core. Okay, this is core, and this is called cladding. Core is surrounded by another medium of lower refractive index, so less refractive index. I'll name it again. Core. Core is made up of more refractive index. This is core. Refractive index more, and cladding is made up of lesser refractive index. Refractive index less. Okay, and both are coated one over the other, and both are transparent, and it is not hollow, it is a solid one. And how do we transmit the light through this? Optic fibers are the cables, transparent cables, solid cables, and they work under the principle of total internal reflection. And they are used to transmit signals over long distances, even in the curved path. They can transmit light in the curved path. How, sir? Now, a laser beam is taken, and if this is the axis of the optic fiber, and suppose a laser beam is incident onto this end, and it falls on this surface, say. So core has got a uniform refractive index, say. It may be having some variable refractive index also. Suppose the light falls on this. Now this angle is chosen in such a way that for this medium, when the light laser beam travels from core to cladding, core is having more refractive index, denser, to rarer, cladding, which is having refractive index less. This angle is chosen in such a way that it will be more than the critical angle. So what happens to this ray of light if this angle is more than critical angle? If this is normal, it undergoes total internal reflection. And here also, this angle will be more than critical angle. Light can't enter into the cladding, lesser refractive index, and rarer medium, it undergoes again total internal reflection. So after a series of total internal reflection, light comes out with almost the same intensity. So you were able to, and for an external person, we feel that the light has traveled in a curved path. So we were able to send a light in the curved path. So this is how the optic fibers work. So they contain a core made up of some material of higher refractive index, transparent but solid, surrounded by another material called cladding and of lesser refractive index. And the refractive indices must be chosen in such a way that when a ray of light is incident at suitable angle, it should undergo a series of total internal reflections and finally come out at the other end. That is a speciality of optic fiber cables. Of course, you might have seen by the side of the roads, you will have some boards like that, and it will be written like this on this OFC, optic fiber cable. If you have such stones on the roadside, the meaning is that Telecom has put some optic fiber cables inside, and it is not a single fiber. And remember, this single fiber cable will be as thin as your hair. Or single fiber cable, only as thin as your hair. They don't put one single fiber cable, OFC, they will put a bundle of cables, and it will be coated with some other materials, because when it is put inside earth, it shouldn't get disturbed from moisture or pressure from outside and water when it is raining. It has to be protected from everything. So we have different types of coatings over it, and finally the cable will be of this much thickness. Actual cable will be inside. There will be a bundle of cables, and we will see that later on. At the end I will show how that optic fiber cables are. So finally it moves out through the cable like this. So optical signals can be sent over a longer distance, and they can be brought in the other side very easily. And this finds a replacement for all the copper cables, because in the olden days we were using copper cables for sending electrical signals. The main problem with the copper cables is copper cables get heated when the current is passing through them, or signals, electrical signals are passing through them. So whatever the signal is received at the other end will not be as strong as the signal which is sent. So every time you need to amplify it and you have to send it back. So it needs a lot of energy, because loss of energy itself is more. Here such a loss of energy is very less. Only the thing is, if you want to add another cable, coupling is a little bit difficult, because this ray of light should fall onto the other cable with the same angle of incidence such that it undergoes total internal reflection, otherwise it is a problem. So coupling the cable is difficult, whereas coupling copper wires is very easy, but it is not so easier. But still, this is more efficient way. You can send the signals for a longer distance without loss. And one of the another applications. So if you are asked to write the answers, what are optic fiber cables? They are the cables which can transmit optical signals over longer distances and even in the curved path. They work on the principle of total internal reflection. Applications: communication, telecommunication, and they are also used in medical field. You have to write endoscopy. Second application of optical fiber cables is endoscopy. Sir, what do you mean by endoscopy? It is a very widely used application. Doctors will have a set of cables. They will, with proper treatment and all, they will put the cables, two sets of cables actually, put it inside the stomach. And proper care will be taken when it is put inside the stomach. Suppose there is something wrong in the stomach. If you have stomach ache very frequently, and if there is anything going wrong inside the stomach, they can get the picture of it. How? So the cables are sent. In one set of cables, they will send the light. That light enters into the stomach and gets spread everywhere. And the reflected light from the parts of the parts inside will be taken through another a set of cables, and it will be given to some electronic equipments, and you can see what is going on inside the stomach. This is a very widely used method of examining the internal organs. So in order to check any problem inside the stomach, the endoscopy method is used, where two sets of cables are used. Light is sent through one, and the reflected light is collected and taken out from another one, and it is displayed in a screen. So to study the internal organs of the human body, we use endoscopy. We use optic fiber cables. So you may have in questions, you read about this, it's very interesting, and you can search it in any of the websites. You will get how it is used to study the internal organs. Then finally, when you view some videos or when you view the some photos, details about this, finally at least you will remember for the exam that what are the applications of optic fibers. It's a very famous application. So only that question will be asked. And another one, optic fiber cables are also used in total reflecting prisms. With that, I will stop once. What are total reflecting prisms? Total reflecting prisms are right-angled isosceles prisms made up of glass. Right-angled isosceles prisms made up of glass. So if I have right-angled isosceles prisms, right angle 90 degree, and if it is isosceles, this angle should be equal. So remaining is 90, 45, 45. They are called total reflecting prisms. What are the uses of these total reflecting prisms? See, glass usually has a refractive index of about 1.5 or so, and its total reflecting angle, critical angle, will be around 42 degree or so. Right? 45 degree will be more than the critical angle. Let us imagine that the critical angle for glass is 42 degrees, say, almost. for this glass. There are different types of glass. If it is 42 degree, what will be the situation? You take a total reflecting prism like this. Okay, I'll put a ray of light like this. Take a ray of light, make it to fall like this. No total internal reflection is possible here. Why? Condition is not satisfied. What are the conditions? Ray should travel from rarer to denser medium. Now this is air, this is a special type of glass whose critical angle is 42 degrees. Any ray of light more than critical angle will undergo total internal reflection. Here it is moving from rarer to denser medium, no question of total internal reflection at all. Moreover, this angle of incidence is 0, so angle of refraction is also 0. It falls here. What about this surface? Draw a normal to that surface. For this surface, this is the normal. What is this angle? This is definitely 45 because this is 90, this is 45, this should be 45, right? 45 plus 45, again 90, so this is 45 and this is also 45. Now is this angle greater than the critical angle? Yes, exactly. This angle is greater than critical angle. So what should happen to this ray? Instead of going out, it undergoes total internal reflection at 45 degrees because you know angle of incidence and angle of reflection must be same. What about here? Sir, is the ray of light traveling from denser to rarer? Yes, first condition is satisfied. Is the angle of incidence greater than critical angle? No, because this is the normal to this surface and angle of incidence is 0, refraction is 0, it moves straight. Now finally what has happened? A ray of light moving like this has been totally reflected and it moves like this. Now did I totally finally bend the ray of light by 90 degrees? Totally the ray of light has been bent by 90 degrees. So total reflecting prisms are right angled isosceles prisms made up of glass which are used to turn the ray of light by 90 degrees. Here only total internal reflection is possible because angle of incidence is greater than 42 degree critical angle. Ray is traveling from denser to rarer medium. Now where do we use these applications? Periscopes. You can search this anywhere. Periscopes where to see the objects which are inside water or somewhere else. Periscopes turn the ray of light by 90 degrees. Okay, now is there any other application? Yes sir, you can turn the ray of light in a different way. Suppose you have a ray of light moving over, okay, you have to turn the ray of light by 180 degrees, yes. Suppose there is a total reflecting prism like this. So isosceles right angle. This is 45 degrees and this is 45 degrees. So second application of total reflecting prisms. Take a prism whose two sides are equal and one side is right angle. Ray of light is incident on this face. No total interreflection possible, falls on the other face. Here the angle of incidence is definitely 45 because this is 45, this is 90, this is 45. Ray undergoes total internal reflection, moves here because this angle and this angle will be same. After reflection, what about here? Denser to rarer. Keep a normal here to this surface. 45 undergoes total internal reflection. Comes here. What about here? Denser to rarer. First condition is satisfied. But for this one, if you draw a normal, angle of incidence is 0. Not greater than critical angle. So moves out. What is the condition here? Ray is turned by 180 degrees. It was moving like this, it has come out. This type of arrangement is used in binoculars. See, we have two eyes, right? And when you just view, you go to the top of a building or a hill, you view the nature. You can view, you can have your visual or range like this. Suppose you want to see the world in a greater range. In binocular, for example, binocular has got two sets of telescope. One which adjusts with your eyes, and outside it will have two sets of telescope. It is in a wider range. Why? It gives a greater view. By normal eyes, if you have normal vision and if you can see a world using binocular, you can have a wider vision. How it is possible? You see, suppose your one eye is here. So it is used in binocular. Suppose one eye is here and another eye is here. So you have only this much width of the eye, but you can receive this ray also. this ray which is coming from somewhere else can be received by your eyes. Similarly, if you have another total reflecting prism here, you can use this ray of light also like this. So this can also be viewed. So to increase the range of vision, you can use the total reflecting prisms which will reflect the light or turn the light by 180 degrees. So this is turning by 180, turning by 90. Third application of total reflecting prisms is to to get the upright image of upright images. So usually some of the images will be inverted in lenses or mirrors. So if you want to get the upright image, you can use it like this. Suppose you have a total reflecting prism like this, 90 degrees, 45 and 45. Suppose in a simple manner I will show it. Suppose you have an inverted image like this. I want to get the upright image. Consider two rays of light. One ray going like this, it undergoes refraction here, and total internal reflection here, moves like this, comes like this. And another ray of light coming like this here, and okay, I will take a different color. So like this, undergoes refraction, undergoes total internal reflection, and comes out here. This produces, you see, this ray of light has been gone up, this has come down, so you will get the upright image of the object. Of course, all these things are just applications. Now know this one, you may be asked for 1 or 2 marks. What is total internal reflection? What is critical angle? What are the conditions for total internal reflections? And what is an optic fiber? Application of optic fiber. What is the principle of optic fiber? And what are total reflecting prisms? Why they are used? And how can you turn the ray of light by 90, 180 and produce upright images? All these may be 1 mark or 2 mark question, but it's an important part. Derivation of relation between refractive index and critical angle. N equal to IC is equal to sine inverse of 1 by n, or n equal to 1 by sine IC. So for problems and all. So we will see some of the aspects which you have explained now by putting some laser light. We will see that, then we will finish the class. Thank you. Now let us see some of the practical aspects of what we have studied in this class. Practically, how can show refraction. So this is a glass slab, rectangular glass slab. Already we have shown the path of the light here. Suppose if I take a laser beam and put it like this, you can see how does it move. So I can adjust the laser beam such that it moves in a particular direction like this in the path which is shown. Now if I remove the laser beam, you can see the shift in the ray in the original direction. So now it is hitting here to the 2 nails and bending. It needs a little bit of, it is moving from here. Now if I remove the glass slab, you can find that its path is entirely changed, right? So this is the direct path without any refraction, and if I place the glass slab, its path will change. Yeah, now it undergoes refraction. Right. Yes, you can see the path almost now. Right. And if I remove this, it moves in the same straight line. Right, so the refraction in a glass slab, you can see it here now. Yes, that is one of the things. And another one is total internal reflection. If you take a liquid and put some amount of colorful liquid into that and mix up it in a dilute form, not more amount of color will make it very dark. Now if I put a laser beam into that, you can see the total internal reflection. See, I have put a laser beam onto one side, the light doesn't come out. It undergoes total internal reflection here at this place, and it returns back to the same liquid and passes out. You can see it from all the angles, and see how I will raise it, and you can see the ray of light undergoing. Can you see that? Little bit of, right? Shall I rotate the laser beam? So like this, you can see the path, right? Can you see the path now? So it undergoes total internal reflection, correct? You can see? Yes. Yeah, now? Yes. So this is one way you can show the total internal reflection. Even in a glass slab I can show it. If I take the glass slab and if I keep it here, again as I did earlier, you can take a beam of light and you can make it to undergo total internal reflection. To some extent I can show it. You can see, yeah. It is difficult to see the path of the laser beam. It doesn't show any path. Yeah, to some extent I can show the ray undergoing reflection, and there is no light here, you see. You can't see light here after refraction. I can see light here after reflection. A small amount of light. So this acts like a reflecting surface. So I can see the light falling on my hands here. If I decrease the angle of incidence, of course I can see the light here. So this is one total internal reflection. And you have studied that optic fibers are the applications of total internal reflection, and they use the principle of total internal reflection. So this is not actual optic fiber. This is used for decoration. You see how the thickness of each fiber here it is. Actual optic fiber cable used for communication purpose, OFCs, they are much more minute than this. So this is used for decorative purpose. Actually this is a single fiber, and this is not hollow inside, and it is very solid, and it allows the light to undergo total internal reflection. So if I put a ray of light here, this torch light here, like this, you can see the tips of each fiber glowing with the color, right? So light is carried through this. Throughout the path you can't see the light because light doesn't come out of the fiber. So, right, it is proper, right? So you can see that. So if I turn it towards your side, see it is like this, right? You can see the light. So this is, you can get it in shops, and all these optic fibers are available everywhere now. That is one type, and here is one more type. You can see this one also, right? So you can pass light through this and you can see that. And some cables are cut here and there, and you can see the light coming out of it, even the smallest one. I think you can see this, right? The smallest one, which and if I stop the light, you can, if I switch off the light, no light comes out. So, and you can even use laser beam. I can put a beam of laser here, and so you can see the light coming out of it, right? Since it is a parallel beam, it doesn't enter through all the fibers. If I change the direction, different fibers receive light, and you can see the light coming out of it. So this is the principle of optic fibers. But you will get very minute optic fibers used in endoscopy and telecommunication. Okay? You can do this, and you can see these effects in your house also. Thank you.